Welcome to the deep dive. Today, we're digging straight into a really big one. It's often called the single most important unsolved puzzle in computer science, the P versus NP problem. And it's not just some academic curiosity, there's actually a $1 million prize attached to it from the Clay Mathematics Institute, one of the Millennium Prize Problems. So the basic idea, kind of informally, is this. If you can check an answer to a problem really fast, does that mean you can also find that answer really fast? Okay, let's unpack this.
Exactly. And to really get into it, we need to define what we mean by fast or quickly. In computational complexity theory, quickly usually means polynomial time.
Polynomial time. Right, so not just raw speed, but how solving time scales as the problem gets bigger.
Precisely. It means the time or resources needed are bounded by, well, a polynomial function of the input size. It scales manageably, not, explosively.
Got it. So how does that relate to P at NP?
Okay, so class P includes all the decision problems that an algorithm can actually solve in polynomial time. Think of P as the set of problems that are quickly solved.
Okay. Solvable quickly.
Then there's class NP. These are problems where if someone gives you a potential solution, a certificate, you can verify if it's correct in polynomial time. So NP means quickly verified.
Ah, okay. So solving versus checking?
That's the nub of it. And we know for certain that P is a subset of NP. If you can solve it quickly, you can definitely check a given answer quickly.
Right. That makes sense.
The huge $1 million question is whether P actually equals NP. Is checking really just as hard as finding the answer in the first place, or is there a fundamental gap?
I like the Sudoku example for this, a big generalized Sudoku puzzle. Finding the solution can be incredibly hard, might take ages.
Right.
But if I give you a completed grid, checking if it follows the rules, that's super fast, trivial almost.
That's a perfect analogy. Sudoku is definitely an NP, quick to check. But nobody knows if there's a polynomial time algorithm to solve any given Sudoku.
Yeah.
It might be NP, but we suspect it's not.
So the effort to find versus the effort to grade, it seems obvious they're different, but proving it.
Exactly. That's the challenge. Yeah.
It seems wild that this question, rooted in polynomial functions, has such huge real-world implications. You hear it called the most important open problem in the field. Why such a big deal?
Well, the stakes are just immense. It touches cryptography, AI, logistics, economics, even fundamental mathematics. And, there's a pretty strong consensus already.
Oh, what's the feeling?
Most researchers, something like 88% in recent polls, and nearly all experts, they firmly believe that P does not equal NP.
Wow, that's strong. So they believe verification really is easier than computation for some problems, that the gap is real.
Yes, the feeling is that this isn't just because we haven't found the right algorithms yet, but that it's a fundamental truth about computation.
But if most experts think they know the answer, why the huge effort to prove it?
Because belief isn't proof. And the structure of the problem is fascinating. We talked about NP-complete problems.
Right, those are the really tough ones.
Exactly.
Yeah.
They are the hardest problems within NP. Think of things like the Boolean satisfiability problem or even that generalized Sudoku we mentioned. They're all, in a sense, computationally equivalent in difficulty. Meaning if you found an efficient polynomial time algorithm for any single one of these NP-complete problems, just one.
Then what?
Boom, you'd instantly prove P equals NP. And efficient solutions would suddenly exist for thousands of other critical problems, optimizing delivery routes, folding proteins, designing circuits.
Okay, let's game that out. Say someone does prove PNP. Setting aside the chaos for a moment, what are the upsides?
Oh, the upsides would be staggering, truly revolutionary. In mathematics, computers could potentially find formal proofs for theorems much more easily. Imagine automating mathematical discovery to a large extent.
Wow.
And logistics. Things like the traveling salesman problem, finding the shortest route visiting multiple cities would become efficiently solvable on a massive scale. Think global supply chains, completely optimized.
But then there's the other side, the immediate hit for, everyone listening. It sounds like it would break the internet, basically.
That's not too far off, unfortunately. So much of our modern digital security public key cryptography like RSA, even symmetric ciphers like AES, and hashing functions, they rely heavily on the assumption that certain problems are hard to solve, but easy to check. Finding prime factors of a huge number, for instance.
Which is a P versus NP type of assumption, right? Checking is easy, finding is hard.
Precisely. If PMP, that assumption collapses. Keys could be found efficiently. Most current encryption would become essentially useless overnight. a security nightmare.
Okay, so that's the dramatic, unlikely scenario. What if the consensus is right and we finally prove P does not equal MP?
Well, it wouldn't cause the same immediate technological upheaval, obviously, but it would be a profound scientific confirmation.
How so?
It would tell us definitively that, yes, some problems are just intrinsically hard. There's no magic bullet algorithm waiting to be discovered for them. It validates decades of cryptographic assumptions and guides research towards, say, better approximation algorithms rather than searching for perfect, fast solutions that might not exist.
So really, it confirms the world largely works the way we think it does computationally.
In a fundamental way, yes.
So what does this all mean then? When we boil it down, P versus NP is really about this gap between, what, solving something and recognizing the solution.
Exactly. Is creativity, that leap to find a solution, fundamentally different from just recognizing it once it's presented? One source put it really well. If P were equal to NP, it suggests there's no fundamental gap between solving a problem and recognizing the solution once it's found.
Which kind of challenges our whole idea of a creative leap, doesn't it?
It really does. So maybe something for you to think about. When you face a really complex task, maybe at work, maybe just figuring something out and it feels incredibly hard to crack, but you know you'd recognize the right answer if you saw it.
Yeah.
Are you just hitting your own limits, or are you bumping up against one of these potentially fundamental barriers in computation itself? It's a fascinating thought.